It's quite something how quickly AI is evolving, isn't it? Moving beyond just text to models that can genuinely interpret and create across all sorts of data types.
Yeah, the really interesting development now is this push towards foundational models designed, right from the start for this kind of unified multimodal ability.
Okay, let's unpack that because we've been looking at some fascinating work. Today, we're going to dig into BAGEL.
Right, BAGEL. It's a new open source foundational model, and it's specifically engineered for understanding and generating across multiple modalities, all in a single framework.
So we're talking one system handling text, images, video together, not like separate specialized tools bolted on.
That's the core idea.
And our goal today, using the research paper Emerging Properties in Unified Multimodal Pretraining as our guide, is to really understand what makes BAGEL tick, how it was built and why it's stirring up discussion in the AI community.
So the paper itself introduces BAGEL as a decoder-only model, and it's pre-trained on this enormous data set. We're talking trillions of tokens.
Trillions. That number is just hard to grasp. And this wasn't simply a huge pile of text, right?
No, not at all. The training data was a really rich mixture. Interleaved text, images, video, and quite diverse web content.
And the researchers argue that this comprehensive and varied data set is fundamental. It's key to BAGEL's capacity for sophisticated multimodal reasoning.
Yes, because it's seeing all these different types of information woven together that lets it make those complex connections.
The paper also makes some strong claims about performance.
It does. The findings suggest BAGEL surpasses other publicly available unified models. That's in both generating new content and in comprehension, measured across standard evaluation benchmarks.
That's quite a claim. Can you give us a feel for the kind of advanced reasoning it can actually perform? What does that look like?
Well, figure 1 in the paper is pretty illustrative. It shows things like free-form image manipulation, predicting future video frames, doing 3D transformations.
And even navigating simulated environments. Wow, simulated world navigation. That definitely sounds advanced. So what was the main driver behind creating BAGEL in the first place?
The researchers are quite direct about it. They state their aim was to try and close the performance gap between academic open models and those very capable but often closed proprietary systems, thinking of things like GPT-4o or Gemini 2.0.
And their strategy was scaling up.
Scaling up, but specifically using carefully structured multimodal data where different modalities are, interleaved, woven together.
And the scaling, it's not just about making things bigger, is it? The paper talks about emerging properties. What's that about?
That's a key concept. The idea is that as you scale up this pre-training with the interleaved multimodal data, genuinely new and complex abilities start to emerge.
So not just getting better at old tricks, but learning new ones entirely.
That's the observation. Abilities that weren't explicitly programmed but arise from the scale in the data structure.
And critically for other researchers, they've made BAGEL open.
Yes, they've released the model's code and the trained weights, the checkpoints. The goal there is clearly to foster more investigation and progress in the wider field.
Let's get into the nuts and bolts then. How was BAGEL actually put together? What can you tell us about the data and the architecture?
Well, a big part of the work, as outlined in the paper, was establishing a new protocol. This was for scalable data sourcing, but also rigorous filtering and careful construction of this high-quality multimodal interleaved data.
That filtering step must be absolutely crucial when you're dealing with web-scale data.
Immense task. And they also specifically incorporated video data. The interesting point there is that video offers unique learning signals.
How so?
You get detailed pixel information, obviously, but also visual concepts, the dimension of time, motion, physics, all things that help build a more grounded understanding of the world.
That makes a lot of sense. A still image is a snapshot, but video adds change, interaction, causality.
And the interleaved format itself, it's inherently quite versatile, isn't it?
How do you mean?
Well, just by its design. Interleaving naturally covers tasks like multimodal chat, text-to-image generation, text-to-video, even editing existing images or video based on instructions.
The paper also mentions drawing inspiration from another model for structuring the data.
That's right, they cite DeepSeek R1. The inspiration was about enriching their interleaved data with content specifically geared towards boosting reasoning capabilities.
So trying to bake reasoning into the data mix itself.
To encourage a better transfer between, say, understanding a complex scene and then being able to generate or modify something based on that understanding.
Okay, so that's the data side. What about BAGEL's internal structure? the architecture.
It uses a mixture of transformer experts architecture, MOT,
MOT, right.
which basically means different sets of its internal parameters, the experts, get selectively activated depending on the type of data being processed at that moment.
So specialized pathways for text, image features, that sort of thing.
Correct. And another important point, unlike some earlier approaches that might have used bottleneck layers to connect understanding and generation parts,
Which could potentially limit information flow.
potentially. BAGEL has what they call a bottleneck-free design. Figure 2 in the paper shows this. It allows for extensive interaction, even over long sequences, between the multimodal understanding and generation processes.
How does it achieve that?
Through shared self-attention mechanisms, these operate across all the transformer blocks, letting different data types interact more freely.
Interesting. And what's the overall size of this model?
BAGEL has 7 billion active parameters. The total parameter count is 14 billion because of the MODI structure.
And it builds on an existing foundation.
Yes, it's built upon the Qwen 2.5 large language model architecture. It incorporates many of the now fairly standard refinements like RMS norm, SWIGL-U activation, ROP for positional embeddings, and grouped query attention.
GQA, yeah. And they added something for training stability, too.
They did. They integrated QK norm into each attention block. It's a technique often seen in image and video generation models, helps keep the training process stable, especially at scale.
The paper also mentions a sort of dual system for handling visuals.
It does. For visual understanding, like analyzing an input image, they use a VIT encoder, a vision transformer.
Okay.
This one's initialized with weights from SIGLEP2, and its job is to process the image and extract meaningful features.
And for visual generation.
For actually creating images or video frames, they use a pre-trained VAE model. That's a variational autoencoder taken from the FLUX model.
And this VAE handles the conversion between the raw pixels and a more compressed, latent representation.
Correct. And importantly, this VAE component is kept frozen during BAGEL's main training phases.
So one part learns to see, another pre-trained part knows how to draw, essentially. How do all these different pieces, the text, the VIT features, the VAE codes, actually interact inside the model?
So they apply 2D positional encoding to both the VIT tokens and the VAE tokens before feeding them into the main language model part.
Okay.
For diffusion time steps, which are relevant during generation, they add an embedding directly to the VAE token's initial hidden states. Then, within the transformer blocks, tokens from different modalities are just interleaved based on the input data structure.
And how does the model know what to pay attention to? Say, if it needs to relate a text instruction to a specific part of an image.
They use a generalized causal attention mechanism. This allows tokens in one segment, say a text segment, to attend to all the tokens in the segments that came before it.
Right.
Within each segment, text tokens use standard causal attention, only looking back at previous text. But the vision tokens, the VIT and VAE tokens, they use bidirectional attention within their own segment.
That sounds like a pretty flexible way to manage information flow across different kinds of data. Okay, so that's the architecture. How did they actually train this thing? What was the strategy?
It was a multi-stage process. Table 3 in the paper lays it out nicely. It starts with an alignment stage, then the main call. Pre-training, or PT, followed by continued training, CT, and finishes with supervised fine-tuning, SFT.
4 stages. What was the goal of each?
The initial alignment stage seems focused on getting the visual encoder, the VIT, and the language model part speaking the same language, so to speak. They mainly train the connection between them using paired image-text data.
Okay, establishing that basic cross-modal link. Then pre-training.
In PT, they introduced the QK norm for stability and made most of the model parameters trainable. This is where they use that huge amount of diverse interleaved data we talked about earlier, trillions of tokens.
Got it. And continued training. What was the focus there?
CT seems geared towards further boosting the visual capabilities. They increased the resolution of the visual inputs.
Higher detail.
Right. And they strategically sampled more of the interleaved data that really required cross-modal reasoning, presumably because the basic understanding and generation were getting solid by then.
And finally, supervised fine-tuning, SFT.
SFT used carefully selected, high-quality data for specific generation and understanding tasks, sort of polishing the model's abilities on targeted examples.
The paper also highlights the need for careful balancing during this unified training. Things like data sampling ratios, learning rates.
That's a really crucial point they make, especially for unified models. Figures 5 and 6 show some experiments on a smaller 1.5B parameter version.
And what did they find?
They found it's critical to balance the mix of generation data versus understanding data. Their results suggested sampling generation examples more frequently than understanding ones work best.
Interesting. More practice generating.
Seems like it.
Mhm.
They also found different learning rates were optimal. Larger rates helped the generation loss converge faster, while smaller rates were better for the understanding loss. So they ended up using separate weighting for those objectives during training.
And it's as BAGEL went through these stages, especially the later ones, that these emerging properties started to become more apparent.
That's what they report. Figure 7 gives a visual timeline. Basic multimodal understanding and generating high-fidelity images, those seem to come online relatively early.
Okay.
Then, abilities like more complex editing and freeform visual manipulation started to emerge later in the training.
And finally,
The final stage showed long context reasoning really starting to benefit both understanding and generation. It suggests a kind of synergy developing between these capabilities that might have been more separate initially.
and to measure these more complex editing skills, they actually built a new benchmark.
They did. They call it Intelligent Bench. It's specifically designed to evaluate freeform image manipulation that requires, complex multimodal reasoning, not just simple edits.
And how did BAGEL do on that?
Interestingly, they found performance on Intelligent Bench kept improving significantly even in the later training stages, like CT and SFT, which wasn't necessarily the case for more traditional, simpler editing tasks.
What does that imply?
It highlights the importance of the visual input stream, the VIT tokens, for enabling these more reasoning-heavy editing abilities. The model needs to deeply understand the image to manipulate it intelligently.
The paper includes some visual examples of this improvement too, doesn't it?
Yes, figures 8 and 9 are quite telling. They show how things improved across checkpoints. For text-to-image, you see the text rendering within images getting much better in later stages.
And for the intelligent editing.
You see the model going from making maybe minimal or slightly off changes early on to producing really coherent, semantically appropriate edits later. It clearly developed a better grasp of the intent behind the edit request.
Okay, so after all this training and development, how does BAGEL actually stack up against other models? Let's talk performance.
Right. So Table 4 in the paper covers multimodal understanding benchmarks, things like MME, MMBench, MMVet, and so on.
And the takeaway.
The main takeaway is that BAGEL generally outperforms the existing open-source unified models on most of these benchmarks. It's even competitive with some models specifically designed only for understanding tasks.
That's impressive for a model doing both understanding and generation. How about the generation side? Text to image.
Tables 5 and 6 cover text-to-image. On GenEval, which is a broad evaluation, BAGEL scores strongly, surpassing leading public generators and other unified models listed.
And the WISE benchmark, that one focuses more on reasoning, right?
Yes, WISE tests complex semantics and world knowledge needed for generation. BAGEL performs well there too, suggesting it has pretty robust reasoning capabilities feeding into its generation. Figure 10 also gives a qualitative sense, showing BAGEL's outputs often look better and follow prompts more accurately than comparisons. Plus, it handles multiple languages and aspect ratios natively.
Okay, strong on understanding, strong on generation. What about the editing capabilities they focused on?
So on Gedit Bench, which is an established benchmark for more standard image editing tasks, Table 7 shows BAGEL is competitive with specialized editing models.
And on their own new benchmark.
On Intelligent Bench, the one testing complex reasoning edits, Table 8 shows BAGEL significantly ahead of the other open-source models they tested against. Figures 11 and 12 provide visual examples suggesting it handles tricky edits more effectively.
They also looked at explicitly prompting the model to think before answering or generating.
Yes, Section 7.4 covers generation and editing with thinking. It's essentially using a chain-of-thought approach. They let BAGEL generate intermediate reasoning steps before the final output.
And did that help?
It did. Table 6 and 8 and Figure 13 show significant performance boosts on both the WISE generation benchmark and the Intelligent Bench editing benchmark when using this thinking step. The qualitative results apparently improved noticeably too.
The paper finishes up by touching on world modeling. What are they referring to there?
This involves abilities that suggest a deeper understanding of how things work in a physical or spatial sense. Through some fine-tuning with more video and navigation data, they showed BAGEL could do things like navigate simulated worlds.
Like we mentioned earlier.
Right. And also rotate objects in 3D space or generate coherent multi-frame video sequences. Figure 14 shows examples.
Does it generalize?
They note it shows generalization in world understanding to domains it wasn't explicitly trained heavily on, like different art styles or even video game environments. They also show that even a smaller 1.5 billion parameter version performs well, hinting at the potential if they scale Bagel even larger.
But it's not perfect. They do acknowledge limitations.
Of course, Figure 17 shows failure cases. It still struggles with things like generating specific copyrighted characters accurately, rendering really complex text within images, difficult human poses, or generating many distinct objects simultaneously correctly.
And for editing,
Complex edits involving, say, swapping multiple objects' positions or making numerous intricate changes at once remain challenging. These seem to be hard problems for current systems generally.
okay, so wrapping up our deep dive into Bagel, if you had to distill it down, what's the core message here?
I think the research clearly positions Bagel as a really significant step forward for open-source unified multimodal AI. The key is demonstrating these emerging capabilities that arise from that large-scale, interleaved pre-training approach.
And it's not just theoretical potential. It delivers strong results across the board, understanding, generation, complex editing.
Absolutely. And the fact that it's open source is huge. It really opens the door for the broader research community to build on this, explore further, and push things forward.
It definitely makes you think. Considering these emerging world modeling abilities in Bagel and just the general pace of progress, what kinds of new applications or, well, new ways of interacting with AI might become feasible when these models gain an even deeper, more nuanced understanding of our physical world?